Sorry. So we start with a summary of week 4. So we looked into exact solutions of fluids last week. Models 1D. And here the answers was to separate out for the calculation of the partition sum of the ideal gas, and the factor having the contributions due to the interactions, which is due to the potential interacting with particles at position xi and xj, which we termed the correction term. And so this was solvable for a 1D nearest neighbor. Yes. And so the reason is why we could solve that is that here the particles are ordered on a line, and so I can easily integrate over the distances between the particles, or I can also just enumerate the probabilities of them being distributed. And so we did this for the specific interaction of the Tonks gas, where we have hardcore repulsion. So for x over a smaller than size a, there's an infinite potential. And so in this case, we could calculate the partition function for particles on a line of a finite size or extent a. And then taking the continuum limit, we could arrive at the gas law, where here we see recover a result from the van der Waals gas, the excluded volume, which means that in the PV pressure volume diagram, for volumes smaller than the particle size A, my pressure is diverging, but otherwise just happily decaying, so there's no phase transition. And we also saw that we get the same result from a lattice gas approach, where instead of having a continuous lattice, space variable x, we consider a lattice, and either the lattice points are occupied or empty. And there, here also taking the continuum limit, we arrive at the same gas law. Then we started into developing a new set of methods by digging into series expansions, which we're gonna build on today. So in series expansion, we considered two different expansions. One, the high temperature series expansion. And the answers was that for the two-dimensional Ising model, we write down the Boltzmann factor, which is beta j si s j, as cos h beta j times 1 plus si sj times b, where b is defined as tanh h beta j. And so this allows us to see that for high temperatures, for T to infinity, V goes to 0. And so what we do is we do an expansion in the partition functions in orders of V, our expansion parameter. And so when we do that, we need to enumerate all terms on a lattice, and we find that actually only terms of s I to the power of ni s j n j s k n k contribute with all n even. So only these terms give a non-zero contribution to the partition function, and they correspond to closed loops on a lattice. So what we did, in fact, was enumerating what are states where I have closed loops or connected closed loops. And we also briefly saw that we can generalize this approach by also expanding directly the exponential, which would lead to this kind of terms of order. This is what we're going to start on Friday. So that was the high temperature expansion. And the opposite end was the low temperature. Series expansion. And here the answers was to say, I know my ground state, and I want to look at what happens if I add perturbations to my ground states. So that means for the partition function, that I have a ground state partition function. And then I add perturbations to it by counting the probability and the energetic cost of spin flips. So these are then the Boltzmann factors of spin flip configuration, where x is e to the 2 for the 2D Ising. It's e to minus 2j beta. The energy cost I have to pay for a bond mismatch. And so now to enumerate these perturbations, we had to enumerate spin flips on a lattice. And here we have just to note that the number of spin flips is unequal to the order in X, right? So if I flip 2 spins, I can have these 2 spins separated out in my lattice. So each breaks 4 bonds, so I break in total 8 bonds, or I can have them next to each other, then they only break 6 bonds. And so the order in X would be how many bonds I break, and that could be 6 and 8, just for the case of 2 spin flips. This can be also generalized to d-dimensional lattice. So just to compare, for a d equal 2 Ising model, the cost of a bond mismatch was x is e to the 2 as the cost of a, let me rewrite, the cost of a spin flip is of a single spin flip is single spin flip is breaking 4 bonds, so that's 2 times 2 4 bonds. In a d equal 3, I would break 6 bonds, right? 2 more for top and bottom. So I can write this as 2 beta j, the cost, and then 2 times 3. So I hope you believe me that this could be generalized to 2 beta j 2d, which we have also, if you read Carter on this, is then enumerated as 4dk, where k is just an abbreviation for beta j. Okay, and so today we're going to use these. Yeah.
2 questions. First of all, in the above unit,
The high temperature.
yes, not on the diagram P versus volume.
Okay,
yeah, how do you know that there's no distribution?
Because it's continuous.
Oh.
So what we know from the Van der Waals gas, so in the Van der Waals gas, we know that at a high temperature, we also have these curves, right? But if we lower the temperatures, we get a plateau, and below a critical temperature, we get these non-monotonic behavior. And so we know that's then this famous, help me out, Maxwell construction, right? That in this area here, we have a phase transition. And so this is a continuous curve, and that's why we know we don't have any bond happening. Yeah.
And the other one, what does it here? Ansatz or?
Ansatz.
Okay.
Yeah, so this is the ansatz for the higher temperature, and this is the ansatz for the low temperature. And so what we did last week was to sort of develop this framework in general for 2D Ising models. And so today we kind of will put our framework into action by first finding exact solutions. I know, boring, but you know, it shows you that it works. Exact solutions for the 1D Ising model. But I think it nicely illustrates of how the method actually works. And then we're going to discover rediscover the self-duality of the 2D Ising model on a square lattice. And maybe or maybe not, we'll see. We'll talk about the dual of the 3D Ising model. on a simple cubic lattice. So that's basically all looking into applications of the low and high temperature series expansion. Okay, so this can be summed into applications of series expansions. So let's look at the exact solution of the 1D Ising. And in particular, we're first going to look at the open chain. So open chain means we have a one-dimensional lattice, which we enumerate from 1, 2, 3 to n. And so we're now interested in the high temperature expansion. So high temperature, remember, we were looking at loops on the lattice, right? Because here we had the setting that only even exponents of the spins would contribute to our expansion in this variable b. So for the 1D system with an open chain, the number of bonds that we have here is NB is n minus 1, right? All of those in between. And how many loops? Yeah, none, right? Okay, like how can you have a loop on a lattice if the ends are loose, right? So and there is no closed loop. And so that's why here the partition function is easy to calculate. If I just write down what we derived last week, it's the number of bonds, states, chain. Crucial V is missing. Remember V was tangent chain. Then we know that this here contributes just 0. So the partition function is just given by the sum over the states of this, like summing over this factor over this factor 1 over all the states. Each state gives, independent of the choice of the states, gives a 1. So we end up with this 2 to the n, and this becomes cos h beta j, and the number of bonds is n minus 1. And from that, we can take the go toward the free energy, which would be taking the ln, the log of the partition function, and we see that this we can then factor out into an independent term and an n-dependent term. Which the second of we can interpret as the surface free energy due to the open chain having these ends. It's also illustrative in the open chain to use this to calculate correlation functions. So if you look at the correlation function, say Sm, Sn, we know that this is defined as 1 over the partition function, summing over all states. e to the beta j, j, si, sj, now sm, sn. And so if I now do my expansion ansatz here, I arrive at, let me just factor out these terms. Just it's here over z. And then we're left with states sm, sn product over the ij's 1 plus si, sj, and me. And so now things change. Remember, only even exponents of the spins contribute. So that means if I take the product of these spins with the 1, both of them have odd exponents, right? Both have an exponent of 1. So this term does not contribute. However, if Sm is, if Sm is equal to Si and Sn is equal to Sj or vice versa, we have both spins with an even exponent of 2, and they do contribute. So we get the only contribution for Sm equal Si or Sj, and Sn equal Sj or Si. This gives a 1 because we just have the partition function up there. Again, this has no contribution because there's an odd exponent. And so the graph that contributes is then the one with where I go exactly from M to N, right? So it's really like the amount of nodes, how many nodes I have between M and N, not having specified M and N. So the only one graph. The one connecting lattice sites N and M, and it's of length. Remember, we always have the exponent of the V was the length of the graph. That's then M minus N, and I'm here taking, because it doesn't matter if in which order I have M and N. And so now if we go back to our partition sum, remember this was a 1, this doesn't contribute. So I only get a contribution from this sum over the states of Sm, Si, Sj, to, looking at the order in V, which is contributing, which is exactly matching those. And then here, the corresponding graph is the one of Vm and N. So I get the correlation function to be simply Sm, Sn, V to the power of M, N. And I can rewrite this as E minus Mn, which is the distance along the lattice, over a correlation length, where now the correlation length follows from the definition of V, which got jotted down up here. So this is the definition of V. If I plug it in to rewrite it as an exponential, the correlation length becomes minus 1 ln of a tanh of beta j. And that agrees with the transfer matrix. And I guess, that's already a moment to celebrate, right? Remember how much effort it was to to go through the exact solution with the transfer matrix of, like, you know, calculating the eigenvectors and the eigenvalues and, you know, doing all that. Whereas here, with the series expansion, very different concept, basically just writing down the correlation function and plugging in this this expansion ansatz, it kind of just drops out because there's only this one graph where I go in between the lattice sides that I'm correlating. And now, okay, so that's the trivial, the first trivial case. The second trivial case is to look at the closed chain. So we have a loop where now I enumerate lattice sides as before, but the neighbor of lattice side n, the next nearest neighbor, is then 1 again. And so here now the number of lattice sides is equal to the number of bonds. So ND equal N, because I'm looping back. So I'm adding the one link between N and 1. And now a partition function looks different, right? Because now I can have a closed loop also for the partition function. Let me just copy down what we had here. So now this goes to the power of N. Again, we're summing over the states. 1 plus Si Sj B. And now the one loop that we can have is the full circle, right? So it's the graph with V to the power of N. And so we that's get to the power of N, and then we have a 1 plus V to the power of N. This we can rewrite a little bit in terms of plugging in that V is tang beta j as to the power of N plus H beta j to the N. Which makes it a tad easier to write down the scaling of the free energy per spin, where we now have ln 2 cos H beta j plus ln 1 plus V to the N over N. And so it's useful to see that this term is really different in structure to this one. Because, sorry, it's in bracket lesson. Because here we didn't have the factor N up here, right? Here we do. And so this tells us that this is really inherent to the system, and there's obviously no surface energy term because there's no surfaces. No surface free energy. Because there are no boundaries. And similarly, we can write down the correlation function. As again, copying down these prefactors over the partition function and then summing over the states. Now Sm is N. 1 plus Si Sj V. And so what is different now? So the one difference that comes in is that on the loop, if so, say m is 1 and n is 4, I can find a graph connecting these two lattice sides that goes this way. But there's also the graph that goes from 4 via n back to 1. So now I have two different graphs that I can sum over that are connecting the two identical spins, so that these two spins have an even exponent and are actually contributing. So these are the two graphs that I find now for the correlation on the closed chain. And so now there are two paths m and n of length m minus n and n minus m minus n. So now in this case, the correlation function then reads v to the mn plus v to the n minus m minus n. And also note for the normalization, the partition function had this 1 plus vn factor in here, right? So this prefactor stems from this prefactor to the number of bonds, right? And this z then doesn't cancel. This term sort of still tracks on 1 plus v to the n. And again, that's a very short route to get to the correlation function of the 1D Ising model. Yet we learned that the one-dimensional Ising models are kind of a little boring because there's no phase transition. And so what we really care about is the 2D Ising models. And so now what we can say is, okay, so we can enumerate these, we can do the high temperature expansions where we know that we only have to find closed loops. So if you keep going and find lots of closed loops, we'll learn more and more about the system as it's deviating from the high temperature solution. And we can do the opposite thing of taking the ground state and then finding like what's the energetic cost of adding more and more spin flips. And we can learn about, you know, how it's behaving as we go from this limit. And so we can kind of estimate, you know, that a phase transition may happen in between, but it would be very cool to say something about the phase transition, right? To know, like, what is the critical temperature at which a phase transition will happen? And what are the critical exponents, right? These are that we really want to get to. And so now, like, magic happens. Like sometimes you have these magical moments that you realize that there's a lot of symmetry in a system. And so this is one of these moments. So that Kramer and Vanier discovered that there's actually symmetry in the system that we can use, and we can actually determine the critical temperature by just having in our hands this high and this low temperature series expansion. And that's the topic of looking at the self-duality the 2D Ising model on the square lattice. So that's hidden but discovered symmetry discovered by to connect high and low temperature series expansion. And so to discover the symmetry, what I'm going to do is I'm going to write down again to you the expansions of the partition functions, one's in the low and one's in the high temperature series for the 2D Ising model on a square lattice. So for low temperature, we had found that we can write this as we have this prefactor to n beta j, which is due to our ground state. And then the expansion has terms of 1 plus, and that's just the amount of different permutations of how I can have a single spin flip. And that contributes to -4 times 2 beta j. 2 beta j is breaking single bond. 4 is the number of bonds that I'm breaking. And if I keep going, then I have contributions of where I break 6 bonds and so on. So in the end, actually, how these partition functions are sort of built together is to have this prefactor from the ground state. And then what I'm actually doing is I'm summing over these islands of spin flips, which gives me these numbers here. And then what I'm actually doing here is I have this energetic cost for each bond, and this prefactor here, the 4 and the 6, this is actually the parameter of my island of spin flips. So for a single spin flip, the parameter is 4, and for 2 spin flips that are next to each other, the parameter would be 6. So this is actually times the parameter of the spin flip island. Okay, so that was low temperature, and now we go to the high temperature. So here we have, again, we have a contribution from what's happening at high temperature, which gives us this prefactor. This was the number of bonds. And then we were enumerating these closed loops, right? And so each closed loops, if I spell this out now and also spell out the V, like this is again counting the number of possibilities of how I can place a closed loop on a 2D square lattice, and each then contributing, sorry, that's a tanh H, beta J, to the length of the loop, and that's 4 in this case. And if I go higher, the next loop size I can have is 6, and so on. So the recipe here is, again, prefactors, copying down. And then what I'm doing here is I'm summing over graphs with which generate loops, and the key is that at every lattice side I only have an even number, of graphs meeting, so that can be 2 or 4 on a square lattice, right? So so I'm summing over all graphs with 2 or 4 lines meeting at any side. And then it's and they all contribute then together, and that's then the length of the graph that gives this exponent here. Okay. So far, you can take this as a short recap of these 2 expansion schemes. But if you look closely, you do see the symmetry. Look at this. These prefactors are the same. This one too. And look, even this. It looks like it has the same recipe. How's that? This is lucky us because we chose the square lattice, by the way. But anyway, hey, it works. This is magic, right? This is what I said. Like, this is a magical moment where you discover, like, whoa, how does it happen? Like, they actually look the same, even though they're describing something very different. So what can I do with this when I discover this? You know, why is this actually? And so this is like we're lucky us because we we chose the square lattice. Because if we take the square lattice, okay, now my drawing skills. What I'm doing here is I'm drawing. Okay, so now the lattice sides are actually the windows in between. So these are the spins. This is where the spins are placed. And so what I want to show you is that if I have a spin flip region, let's say looks like that in an ocean of spin pluses, then for the more pluses, then the boundary of the spin island, which is this one. Maybe I need just a bigger pen size. Let me just, oops, yeah. Nice. So the boundary of the spin flip island, dip, 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 dip. That's, if you look at it, it's again a perfectly acceptable graph if we were to sum over graphs with 2 or 4 lines meeting at any side, right? Because that's perfectly what's fulfilled here. So there's a correspondence in the parameters of spin flip islands belonging exactly to the class of our acceptable graphs. And so that's the magic that hits here, so that this is the symmetry that we're building on. Write this down. Oops, and I need to go back. Thank you. Yeah, the boundary. So this tells me that there's a way how I can map between these 2 series. So, because the only thing that's different is that obviously what I'm doing here is I'm taking something different into the exponent, right? But what I could now say is, like, you know, there's a mapping. I can define a beta J tilde that happily maps onto this tanh function. And then if I perform this mapping, I can go from the low to the high temperature series. Yep.
The length of the graph, we mean the number of bonds that there are in the graph, or for us.
Yeah, so it's depending on where are you? Are you in the high temperature series or in the low temperature series? Okay, so in the high temperature series, we're interested in graphs that have so that meet in 2 or 4 lines. So for the high temperature series, I don't I'm just counting graphs. So there's no, I don't think about spins. I'm just thinking about graphs.
Like for example, because why 4? Because there are.
Oh yeah, so
because loop is
exactly. So this one, yeah, that's the 4. And that would be the 6.
Yeah. Okay.
So but so the difference is these here, these are my lattice sites, right? So I'm drawing graphs on lattice sites. Whereas in this drawing, these are the lattice sites, right?
Yeah.
So here, these graphs would correspond to graphs along the bonds of the lattice. So what it turns out is that the dual lattice, have you ever heard of dual lattices? Okay, maybe. So the dual of a square lattice is a square lattice. So if I construct a lattice of a square lattice by basically defining a line perpendicular to each bond on a square lattice, and I look at, what's the lattice I would generate just by this rule of taking a bond and always drawing a perpendicular line, and when 2 perpendicular lines meet, that's defining a new lattice node. Then for the square lattice, I arrive at a square lattice again, right? So say this is my lattice, and I'm drawing the dual by constructing it by just drawing the perpendicular ones. Then the green lattice is again a square lattice. So that's why choosing the square lattice was key to identify the hidden symmetry. And then we will see that once you have this idea, once you found this concept, even though in a very simple case, it's very powerful, because then you can start to think about, like, does this concept actually also apply to other lattices? And we'll see that it does, maybe Friday. But that's the key. And so already here noticing that these are different things. So the low temperature series expansion, this is spin flips, this lives on the lattice sites. And here the high temperature series is counting graphs, connecting lattice sites, but it's equivalent in the dual lattice of looking at the bonds, right? So I'm just basically tracing out I'm here tracing out the bonds of these lattice spin flips. And so from the mathematical level, I would say, like, okay, there's a function of how I can perform a mapping. So we define a function g to rewrite the series as, and here I'm rewriting ln, taking the normal logarithm. Then I get 2 beta j plus a function g e to the 2 beta. Okay, and this is the moment where it's actually handy to define beta j as k, because then it's easier to say this is, oops, k tilde. And that should be equivalent to ln, and let me do this here too. K tilde, ln 2 plus 2 ln, these are just the prefactors, okay, plus g of tanh h k, such that these are equivalent, right? So if I map the k tilde to the k, I should be able to write this down, noting that this is the low temperature expansion, and this is the high temperature. And so the duality that I can do this mapping condition is that e to the minus 2k tilde is corresponds to this tanh h of k, right? Which means that k tilde is minus a half of ln of tanh h. And so this means that I have a mapping between k tilde and k that's given by this function. If I plot this function, it looks something like that. So there's a continuous mapping between k and k tilde. K here describing the high temperature expansion and k tilde the low temperature expansion. And this mapping now really allows me to entirely map the low temperature series onto the high temperature series. And let me define this mapping as d of k. And I can obviously map from low temperature to high temperature and then perform the same mapping again to go back to low temperature, right? So I can entirely connect pairs of points by going from performing this mapping twice on k, I should be back to k. But what this means is, and now let's just write this down. Is if I start with sin 2k, then this I can rewrite as 2 hyperbolic cosine. Sorry, this is just trigonometry, right? But it's useful to see cos hk, which I can then rewrite as 2 tanh k cos square k, which I can rewrite as 2 tanh k over 1 minus tanh square k. And so what I'm getting here is now that I'm rewriting the tanh k here. I rewrote the sin k 2k unmotivatedly into terms of tanh k. The reason is because now that I have this tangent hyperbolicos, I can perform the mapping to rewrite this expression as 2e minus 2k tilde 1 minus e minus 4k tilde. And that I can now rewrite by dragging out the upper one. And then I get e to the 2k tilde minus e to the minus 2k tilde. Haha, this is, we can put back into a hyperbolic sign to see that this is sine hk tilde. So by performing all this math, I found a symmetry relation between the couplings that sin hk, sorry, 2k, and there's a 2 here too, I'm sorry, 2k sin h 2k tilde is equal 1. Which we're going to use. And now okay, so now we discovered, okay, there's some symmetry and we can map them onto each other. And now we're going to use it because our goal was to learn about the critical behavior, right? And so what this mapping now allows me is, okay, I can map any low temperature series to any high temperature series, right? But that means if I have a singular, like if I perform my low temperature series expansion and I get to the critical point, at the critical point, the behavior should be, there should be singularity, right? And if this is the case, then, and I can map the low temperature to the high temperature, then the singularity should map too, right? So then I should have a singularity in the high temperature series expansion as well, right? And so what I need to do is like search for, the singularity in this mapping, and I will find my critical temperature. So in words, if now my mapping G of K is singular at a critical KC theta J, then it must be singular for the tilde one too, for the back one. And so since the free energy is in principle analytic, except for at criticality, we have then this relation being true. So we have 2 Kc is equal tan H of Kc. So the mapping, they have to map onto each other. Like the critical points are the only points that really have to map onto each other. Of the I'm always mixing them up, of the low temperature and the high temperature series. And so now by just putting them equal here, we can now solve this equation consistently for Kc, and that gives us our critical temperature. And again, we play with trigonometry, rewriting this as E minus 2 Kc over 1 plus E plus 2 Kc, no, minus 2 Kc, and there's the plus. That we can rearrange as plus 4 Kc I have a -1. I don't know. Mistaken my notes. Let's see how this works out. And then this is
Sorry. Kc is equal from the both side of the equation. Like there's
so what we say is that the critical point has to map onto itself. So that's the mapping. I'm just looking for a sign error and I can't find it. You can help me. So this is our mapping, right? And what we say is that at the critical point, this is the only singularity that we should have. And so if there is a singularity, then the singularity has to map onto itself. Because otherwise we have more, right, than one singularity. If it, because the singularity would be available in both of them. And so at criticality, these are exactly the same. The couplings, the critical couplings should be exactly the same under the mapping. And so we're just setting this equal, and I'm losing a minus. I have a minus sign in here, and I can't find it. Let me put it down in green, and then we can check independently. But this is what we need to find e to the minus 2kc is then solved by 1 plus minus square root of 2. And so the one that counts is the plus 1. And so we find here that then I have a critical temperature of critical coupling of minus ln 2 minus 1 at 1/2. Sorry. Which is equal to 0.441. And this is indeed vertical temperature. Now remember that Kc is J over beta Tc. So it works. And so just to visualize one more time, so what we're doing here is that if we look at the couplings that we're mapping, what we're doing is we know that we can sort of map the low temperature to the high temperature all along. But there's this one point in between, the critical point, that has to map onto itself. And so by knowing the mapping, we can actually find the critical temperature, and it's really in agreement with numerical simulations. So far on the Celebrate, the downside is, however, we only have the temperature. We have no scaling relationships. We have no critical exponents. But, you know, but no critical exponents. Okay. And so I take it the square lattice was very incremental to actually find this mapping, because it's self-dual. But in fact, you can find dual lattices of many other spin systems and perform this task. Like the XY model, its model, and so
on. Question?
Yeah.
How would I know from this expansion that I, like, for example, if I don't know anything about my system, why do I know that there's only one phase transition? Because, for example, in water, I mean, water is a more complicated system, I know, but if I do a low temperature expansion and a high temperature expansion, I'm going, like, there are two phase transition between of my two series. So how would I know a priori that this method works in the case that there are two or more? How would I see that?
So we use the series expansion for the case where we can work on a lattice. And you will see that already 3D lattices are much more challenging, but I hope I get this across, that there is a duality that you can use. And we were able to write down the interaction, right? And so with your water, you have a more complicated interaction that will make it hard for you to write down this expansion in the first place.
Okay.
So it's something that we can use for spin systems. And then why is this still useful is because we can by solving these spin systems where this method applies, and knowing universality classes of other systems, we can extend our results to this whole class of of systems that we learn about. But I agree, like, there's always limitations to methods, but hey, we learned something about two-dimensional systems, right? Which up to, I don't know, on last Friday, which is already like already November, we'd only been dealing with 1D systems. Right? Yeah. Okay, and now the 3D system. So this requires a little more graphical thinking. So dual of the 3D Ising model on a simple cubic lattice. Okay. So graphically speaking, what we're doing in the low temperature. Let me start by like looking at the expansions, or giving you the expansions of the low temperature, the high temperature now for the 3D Ising model. Still supercubic, so like a square lattice in 3D. So low temperature series expansion, again, we're flipping spins. So, but now if I flip a spin in 3D, I need to consider this whole box of bonds that I break. And similarly, if I flip to neighboring spins, I have to consider these adjacent boxes and how many bonds they're breaking. And so if I enumerate that, then I find the following expansion. Which still has exactly this this kind of principle of how to construct this expansion, namely we're summing over islands of spin flips, and we now have -2 beta j times the area of the boundaries. But now these boundaries are islands boundaries, sorry. But now these boundaries are these cubes, right? So now we're summing over cubes of islands. And at the high temperature, we still enumerating graphs. So graphs means like we still counting loops. So we're doing this. We're still counting loops. And so you may already from the visualization see that this nice mapping may not nicely work out anymore, right? Because obviously these cube areas, they are geometrically very different from these loops that I'm drawing on the lattice. Which obviously now these loops can be like in principle, me and 3D drawing skills, they can be bent in 3D shape, but they're still these planar objects in a sense, right? And so if I give you now the expansion, we get which follows again this recipe we had before. We'll be summing over graphs with 2, 4, and actually now we also have 6 possible, because we're in 3D, 6 lines per any lattice site. And then here it's to the power of the number of lines. And so where you see that it breaks down is already that now on a simple cubic lattice, one spin flip, like just an island of consisting of a single spin, breaks 6 bonds, whereas a loop is still connecting for tracing out 4 lattice sites. Okay, so and also obviously the p factors now don't, they don't match anymore. Like, what shall we do? So indeed the sums here are different. Okay, but we learned from the example of the 2D lattice that conceptually it is possible. So what else do I need to add here so I could rescue this? And so the approach now is to say, maybe it maps to another Hamiltonian, and I have to restructure the Hamiltonian such that I find a dual. So the dual is not the lattice, but the dual is really a different dual Hamiltonian. Is there? High temperature. Whose high temperatures reproduces the low temperature terms of the 3D Ising model. And indeed, there is. Okay, so what I'm doing, so I want to find another Hamiltonian where summing over doing the high temperature expansion, which means that I'm tracing out tracing out graphs, would actually reproduce the geometrical structures of these cubes that make up the terms of my low temperature 3D Ising model expansion. And so the solution is to construct a Hamiltonian which has so-called terms that contribute to plaquettes. So what is my plaquette? Is like this is. Did you know that there's a certain age until which you have to learn how to draw in 3D? And if you haven't done this, and it's like, I don't know, 7 or 8 or something, if you never draw a cube at that age, you won't make it. Like, it's something that your mind actually, that you have to see it. My mom had a very rough time as a child because nobody sat down with her and told her how to draw a 3D cube. She became a math teacher, so I bet you she was early on telling me, like, but I had no idea I would need it for my job so much. Oh my god. Okay. No, it's true. Like, and now they do it in school. They make sure that you learn how to to draw them, because it's like how it's very hard to learn certain sounds in languages that you haven't heard, because you can't just distinguish it, right? It just doesn't mean anything to you. Okay, so trust me that this is meant to be a regular lattice, but okay, so what we do now is to create these plaquettes. We put spins on bonds and couple 4 bonds into a plaquette. So we put these up, sorry, okay, yeah, maybe. So this is these are the lattice sides, right? These vertices. And now I put spins on the bonds and I couple them into a plaquette. Now I created a planar object as my plaquette. And so now if I want to couple these plaquettes, again, the rule being that the plaquettes have to sum up into you know, even exponents contribute. Now these plaquette lines or loops, plaquette curves, graphs, this is equivalent to summing over the area of faces as required for the high temperature series of the plaquettes. And so the second thing that I need to do is I have to adjust the partition function into now summing over, and I call them sigma, these plaquettes, e to the k, summing over plaquettes, and I'm coupling 4 of them together. Okay, 1 plaquette, 2 plaquette, 3 plaquette, 4, such that my expansion then looks like summing over the spins in the plaquettes, taking plus minus all the put in plaquettes. And then I have a 1 plus tanh k times tilde sigma p. So I have this thing that I couple 4 of them, and that's how I go into this. I add this dimension in a sense. Now I can do, in looking at the mapping, I actually arrive this high temperature series expansion maps onto the low temperature original Ising model expansion with this still being the relationship between the coupling constants as before. And so this is a way of how I can generate this mapping. This is obviously not exam material, but it would be fun to see, right? I mean, you're studying physics and have to pass exams, I hope, right? So here you find an example of what's called a Z2 lattice gauge theory, which so the above is an example of Z2 lattice gauge theory. And the general rules to generating those are I place Ising spins sigma I equal plus minus 1 on the bonds, the lattice. And I hope now this makes sense to you, talking about the square lattice in between. We did the same thing, right? We went to like actually the bonds of the lattices to construct a dual lattice, which happened to be a square lattice again. So that's why it wasn't like so obvious, but we actually did the same thing for the square lattice. And so here it's the general thing, except that now we have to that the dual Hamiltonian looks different because we need to we need to couple these spins into the plaquettes. Is K summing over all plaquettes. And so this mapping has symmetries, the system. Also our square lattice before had a global symmetry. You can, the global symmetry is that for what are we doing, it doesn't matter if our ground state is all spin flipped up or all spins flipped down, right? So nothing happens if I flip all spins all together. So under this transformation, as long as I flip all spins, the physics stays the same. It's a global symmetry. But now these plaquettes, they also have a local symmetry. Because what I have in the end, if I, okay, let me take, so this is my lattice side, and these are my, my spins put on the bonds, right? So what I can do now is, if I flip all of these spins emanating from a single bond side, then the energy is unchanged. So how can we see this? Where's the here? So because all these go together, right? The plaquette is summing over all all four spins. So if I change all that are next to a side, and the plaquette was defined as, you know, summing over these loops. Again. So if I flip two of them, the product of both of them is unchanged, right? If I take the product of four spins, and I change two out of the four, nothing changes in the energy. And so that's because here, like the spin flip that I'm performing is a local one. It's a local symmetry that I have. So in words, G is unchanged. And so now it's getting tricky because that's actually, if we have such a local theory, so-called Elitzur's theorem tells us that there shouldn't be there's no spontaneous symmetry breaking with a local with such a local with such a local symmetry. So I can't have an ordered state next to, like I can't have an ordered state if I have such a local symmetry, because obviously I can add disorder to my system by flipping spins, and it doesn't change the energy, right? So how am I supposed to have an ordered state then? So Elitzur's theorem says there's no spontaneous with a local symmetry. Reason being, because of local symmetry, the energy cost of a spin flip is finite. Oops. Even in the presence of a symmetry breaking, like in a flat field. Nope. Here for the cubic Ising, this cost would be 6H. And I would expect a continuous change of magnetization as H goes to 0. We have a problem, right? I mean, we found that in the square lattice of the 2D Ising model, there is a critical temperature, right? So there's a critical temperature. So we have spontaneous, we have a critical temperature below which we find an ordered phase. And now we go up in dimension, we go to 3D. And this theorem tells us, okay, wait, you have a local symmetry here. Like you shouldn't have you shouldn't have any phase transitions. This, you know, and this is not what we expect, because we remember the argument of the lower critical dimensions. The idea is that at lower dimensions you may not have phase transitions, but as soon as you reach the dimensions at which you start seeing a phase transition, then for all higher dimensions you would expect this phase transition. So something went wrong here, right? So there has to be a rescue. So where, okay, and that's just a little bit of writing. Give me 2 more minutes. So where does the 3D Ising model phase transition come from? And so here I won't go into details. I'll just give you a few words of how you can solve this paradox. And the solution is that there's a singularity in the partition function, both in the 3D Ising and its dual plaquette thingy, noticeable by different asymptotic decays of the correlation functions at high and low temperatures, and in between these different correlations functions, you can find the phase transitions. I don't expect you to follow this, but you can read this up in Carter. It's just a few words that saying, basically summing up, you can go into the depth of this mapping and look at the properties of this mapping on 3D Ising model, and you will find flaws which indicate that in between the different dynamics that you can see in this mapping, there is indeed a phase transition possible. That's a short word. I'm just copying down what Carter says. So all is good, and we do indeed have a phase transition in the both in temperatures, phase transition marks change between the two correlation functions. And that's it for today. Thank you.